Hello and welcome to another episode of Aquarium School, brought to you by the Aquarium Vet. My name is Dr. Rob Jones. I'm one of the members of the Aquarium Vet team, and in this episode of Aquarium School we're going to look at carbon. And what we want to look at is, first of all, how is carbon made? How does it work? When should we use carbon? And what are the advantages and disadvantages of carbon in our aquariums? A little bit of chemistry. It's element number 6 on the atomic table, and it's the fourth most abundant element in the universe. Many things contain carbon. And it actually makes up 18.5% of the mass of the human body. There's your bit of trivia for today. It comes from the Latin carbo, which means coal. And it's also important to remember that carbon comes in many forms. It's coal, it's diamonds. You know, diamonds are a girl's best friend. That's carbon that's been heavily compressed, through to graphite, which is like charcoal and can be used for writing, like in a pencil. When we look at the type of filtration that's possible in our aquariums, we have mechanical filtration, which will remove the suspended solids. We have biological filtration, which will remove the nitrogenous waste, and we've talked about that in our presentations on the nitrogen cycle. And then we have chemical filtration, which is what we're talking about today. And chemical filtration is used to remove dissolved organic and inorganic substances with a variety of processes. And it includes carbon, which we'll talk about soon, but it also includes things like ammonia binders, resins, foam fractionation, or protein skimmers as they're also called. And we talk about those in other presentations. Now, according to an ancient Egyptian papyrus back as far ago as 1550 BC, so we're talking 3,500 years ago, carbon was actually used for medicinal purposes. And Hippocrates, the Greek physician, and that's where the Hippocratic oath comes from that the doctors take, a little over a millennium after that 1550, he was using it also. It was well documented. And today, both in human and pet medicine, it's actually used, taken orally, for adsorbing toxins in emergency rooms. So if someone was to take some sort of toxin or poison, they often are given charcoal, and in dogs they'll be given charcoal into the stomach and flushed out to absorb the toxin and get rid of it from the body. And the other thing that's used is that charcoal tablets can be taken by people to reduce flatulence because they absorb all the intestinal toxins. Now, in the aquarium industry, for many years, it's been seen as the magic bullet to remove a whole lot of toxins from the systems. And it does have some very useful properties, but there are still some reservations. The problem that I see is that in a lot of cases, it's permanently present in a lot of systems, and we'll come back in a little while as to why that is not ideal. But what it does do is that it not only is very good at removing toxins, but it's also going to remove a lot of vitamins, trace elements, and amino acids from the water. And removing all of these can have a negative impact on fish health, and especially if you're doing a reef tank with corals. Now, activated carbon is the form of carbon that's usually used in our aquarium situation, and it's made from plant-based materials. So we're looking at bituminous or lignite coal, from peat, from wood, coconut shells, other nut shells, and olive pits. And olives have pits and not pips. In some cases, it's possible to use animal bones, but the type of carbon that is made from using animal bones is very inferior, and to be really honest, it isn't used at all. Now, how is the carbon made? It's a two-stage process. The first is dehydration and carbonisation. So what happens? You take your raw material, whether it's the coal or the coconut husk, whatever, and you heat it. in an oven in a very low oxygen level. And so you start off at about 170 degrees centigrade to remove water. And remember that 100 degrees centigrade is the boiling point of water, so you're getting rid of the water. And then you really put the temperature up very, very high to 400 to 600 degrees centigrade, and that produces almost pure carbon. Everything else is burnt off. And by using that low oxygen and high temperature environment, you're actually preventing the product from burning. And so you end up with a carbon structure that's got a lot of pores, and it's the pores in the carbon that help it to do its work. The second stage is what's called activation. And so after it's been through the carbonisation, you have steam at a very, very high temperature, 750 to 950 degrees centigrade. And what happens is as you treat the remaining product with the steam, you'll get gases leaving the carbon, which include carbon monoxide and hydrogen gas, and you then end up with that very, very porous carbon structure. It is possible to use chemical activation with various acids and bases, but generally it's the steam process that is used. And what that then does is it produces all these pores, and you've got different sizes of pores there. You've got micropores, intermediate and macropores. The micropores are less than 0.2 of a nanometer. The nanometer is 1 billionth of a meter. So we have a meter, a thousandth of a meter is a millimeter. We then go to a millionth of a meter, which is a micrometer. Then we go to 1 billionth of a meter, which is a nanometer. So you have micropores, which are less than 0.2, all the way up to macropores of 5 to 10 nanometers. The most effective activated carbon has a whole range of these different pores of different sizes so that they can take up the toxins. And what happens is, because you have all these pores, it actually creates an incredibly high surface area inside the carbon to be able to take up the toxins. And so if you take 1 kilogram of activated carbon, it's going to have a surface area of 1 by 10 to the 6 or a million square meters. Now, a million square meters is 100 hectares or 247 acres. So you've got 247 acres of surface area in a 1 kilogram bag of activated carbon. And as a general rule, the finer the grade of activated carbon, the higher the surface area will be per kilogram. So it comes in 3 different sizes. From smallest to largest, you've got powder. You've got a granular activated carbon with a grain size of greater than 0.1 of a millimeter. And then you've got pelleted or extruded activated carbon. As the size reduces, the surface area increases, but the problem is that the powdered form has some issues. So it's very difficult to use. It may escape out of the canister into the water because it's so fine. And also because it's so fine, it tends to pack together. And so you get a greater head loss through the canister that's got the carbon, and that means you need a higher pump that can pump through that compressed powder. So as a general rule, the most commonly used carbon form that you will find and that's used in the aquarium industry is called granular activated carbon, GAC. It's that mid-size carbon. If we look at that picture on the left, we've got some granular activated carbon. What that is on the right, that is supposed to represent the microscopic view, if you like, looking down a piece of carbon where you've got all of these holes, and the little black dots are the toxins, which sort of end up in the pores, and the carbon adsorbs them on the surface. And we'll talk about how the carbon actually works in a second. So if you take a filter and you fill it with activated carbon, it will have some mechanical and biological filtration because it's going to remove some of the material that's within the water, and eventually your carbon will get covered in nitrifying bacteria. But what happens is, as that biofilm forms, it clogs up the carbon, and also the suspended particles will be taken up. And so that dramatically reduces the chemical absorption process. And if you are going to use carbon, it should only be used as the end stage in the life support system. So you should have any mechanical filtration and any biological filtration used before the water goes through the carbon, so that it ends up being only used for its chemical filtration properties. And what we use it in aquariums is for, number one, colour removal. So any yellowing from tannins, where you've had maybe logs submerged in the display and you get that yellowing because of all the tannins released by the logs, the carbon, the GAC, the granular activated carbon, is very good at removing that. It will remove any residual oxygen. So if there's any ozone byproducts or any chlorine, got to be obviously not very high levels, because otherwise you're going to kill all the fish. But carbon is very, very good at removing those. Very good at removing any chemotherapeutic. So any drugs that you've put into your system, including copper, the granular activated carbon will absorb those and remove them. And where it's predominantly used is it's very good at removing chlorine and chloramines that are present in municipal drinking water. So it's very commonly used in the pre-treatment of water before it's put into our aquariums. And in another presentation, we talk about, chlorine and chloramines in municipal drinking water and the problems that you can have associated with them. Very important to note, the nitrogenous compounds, the ones that are in the nitrogen cycle, which are ammonia, nitrite, and nitrate, are not removed by carbon to any extent, and the same for phosphates. So if you have a biofilter issue, putting carbon in, unfortunately, will not be fixing the problem. So how does the carbon work? One of two ways. The first is adsorption. And adsorption is the binding or the adhesion of an adsorbate, which can be an atom, an ion, or a molecule, which are the toxins, to the surface of the carbon. And this is where it goes down into the many pores. Remember, we've got that high surface area, and so the toxins will go down. It could be also vitamins and amino acids, as we talked about before, and they'll go down into the pores in the granular activated carbon, and then adsorbed onto the surface. And so the adsorbate may be either a gas, liquid, or solid form, and then it binds to the adsorbent, which is our activated carbon. The second is some catalysis. And this is what happens when you've got ozone, chlorine, chloramine, bromine. There's actually a chemical reaction that happens at the surface of the carbon. And so you gradually get a breakdown of the carbon due to this chemical reaction. And what happens is that the chlorine or the chloramine oxidizes with the carbon, and you end up with chloride ions being released, which are non-toxic. But over time, it will progressively use up the carbon. So with time, the effectiveness of the granular activated carbon diminishes because all the pores are taken up and there's no vacancies. So it's like a hotel where there's a no vacancy sign up. It is possible to regenerate carbon if you use high temperature and high steam and high pressure. But to be really honest, you are better off, I think, to discard the carbon once it's been used, dispose of it responsibly, and at all times follow the manufacturer's recommendations. Now, I will say, as a general rule, I do not like or in any way suggest that granular activated carbon be in systems permanently. I think it can create problems, and we'll come to that problem in a second. How I think it should be used is on an as-needed basis when there is a problem that's occurred. You've got a possible unknown toxin, or you've put in a chemotherapeutic, some sort of drug treatment, and you want to remove it. That's when I like to see carbon used. And one of the reasons that I don't like it is that there's been an association with head and lateral line erosion, HLLE, in fish. There was 2 papers that came out in Marine Tangs quite a few years ago, which showed a clear connection with the use of carbon and the development of these head and lateral line erosions. It's also known as head and lateral line disease or hole in the head disease. And here we have a fish showing the sort of erosions. This is very advanced. This was an aquarium that I visited in China, and I looked at their ocean tank, and there was a whole lot of fish like this. And I turned to the curator and I said, "Do you have carbon in your system?" And he looked at me and said, "Yes, how do you know?" I said, "That's the problem with the fish. If you can take out the carbon from the system, those fish should recover. It is a reversible change as long as you remove the cause of the problem." Now, we still don't know exactly why. It's either because the carbon takes out all the micronutrients from the water, all the vitamins and minerals, amino acids, etc., so there's a nutritional issue, but it's also possibly that the tiny bits of carbon, the dust from the carbon, if you like, gets down in the pores of the head and lateral line system and causes this effectively a dermatitis reaction. But it is reversible. If you remove the carbon from the system, as they showed in those 2 studies, the problem does go away. So the best form of granular activated carbon is from the bituminous or black coal, which is a relatively soft coal. You use it in one of 2 ways. You put it in a contact chamber, and that's probably the best way. That could be a little filter canister right through to a big sand filter, which you fill with the granular activated carbon. And if you really want to remove a chemotherapeutic, you're better off to put it in a contact chamber and have the water flow through the carbon. It's possible to just get a fine mesh bag and put the carbon in that and float it in the top of the tank near the watering flow, and I've seen that, and that's certainly better than nothing. But as I said, if you know, from our studies where we've put chloroquine in tanks and we want to remove the chloroquine and we're actually measuring the levels, we've found the best way is actually using the carbon in a contact chamber. You will get far better results. When you start using your granular activated carbon, always wash it first to get rid of any dust that's on the GAC. Very important not to use tap water, because that tap water will have chlorine in or chloramines in it, which will inactivate some of the granular activated carbon before you even started. So if you're going to wash your carbon, and you should, use either distilled water or reverse osmosis water. And as a general guide, all carbon should be discarded after 4 weeks. So please don't have it in your systems permanently because of the problems that we've discussed. And if you're using it, say, for pre-treatment of town water, either for your freshwater systems or to mix up with seawater, where you're wanting it to remove any impurities, particularly the chlorine and the chloramines, every 4 weeks the carbon should be thrown out and started afresh, because as we discussed, all those pores get filled up and its level of activity decreases substantially. So there we are. We've gone through carbon and how useful it is in aquarium situations, and we look forward to having you at the next Aquarium School presentation. Thank you.